I'd like to present how to assess the glass fracture load distribution by incorporating the invalid test results. Glass has been increasingly regarded as a structural element in the building. Therefore, the glass fracture load has become a key consideration for ensuring the structural safety. The co-axial double ring test is one of the most popular tests for assessing the glass fracture load distribution. During the CDR test, a glass sample is placed between an outer ring and an inner ring. The failure of glass is preferred governed by the surface floor distribution, and as the maximum tensor stress develops inside the inner ring area, therefore the fractures from this area can accurately reflect the surface floor distributions and therefore the glass fracture load. So for the test where the fractures initiate inside the inner ring, they are denoted as the valid tests, and the results of these tests are called the valid points in this study, and on the contrast, they are classified as the invalid points. The ASTM C1499 standard requires excluding invalid tests and at least 30 valid tests. However, these invalid tests still contain the information that can be exploited. Therefore, this study proposed a Bayesian inference-based approach to extract and incorporate such information for characterizing the glass fracture loads. So, in total, there are 3 different methods to characterize the glass fracture loads. The method 1 is the standard method, which considers only the valid points and fits a variable distribution to the experiment data. The method 2 and method 3, they both utilize the Bayesian updating procedure. However, for method 2, it only considers the valid points for the Bayesian updating, and for method 3, it considers both valid points and invalid points during the Bayesian updating process. The Bayesian procedure is based on the Bayesian theorem as recommended by the ASTM standards. The variable distribution is suggested for characterizing the glass fracture loads, as the variable distribution can be expressed in terms of mean and standard deviation. Therefore, these 2 parameters are considered to be updated in this study. The posterior distribution here represents the updated distributions of mean and standard deviation after taking the experiment data into consideration. However, the likelihood varies for the valid points and invalid points, as valid points reflect the true glass fracture load. Therefore, the likelihood of the valid point can be expressed as PDF of the variable distribution. However, in case of the invalid tests, the glass fractures before reaching the true glass fracture load, which reflects a censoring process. Therefore, the CCDF of the variable distribution is applied as a likelihood for the invalid points. The proposed methodology is then applied to an existing dataset for 2 different testing temperatures. The number of the tests is driven by the code requirements, at least 30 valid tests. Therefore, there are 14 and 30 invalid tests for these 2 different temperatures respectively before obtaining 30 valid tests during the CDR experiment. The distributions for the experiment data and their fitted variable distributions are also displayed on the figure right. So the graphs here show the posterior distributions of glass fracture loads compared with the reference distributions. The red curves here reflect the method 1. The green curves here reflect method 2, which consider only valid points for the Bayesian updating. The blue curves here reflect method 3, which consider both valid and invalid points for the Bayesian updating. From the left graph, we can see that there is an increase in the spread of the posterior distributions after considering the invalid points. Therefore, we can conclude that there is a bias in the test procedure where the invalid points are not considered, and this makes sense, as the valid points can only tell us can't tell us whether the glass samples can withstand a higher fracture load, and the stronger glass samples have a higher chance to be regarded as the invalid points. Therefore, ignoring these invalid points will result in a downward shift in the posterior distributions. From the right figure, we can observe the changes in the 5% quartile of glass fracture loads for these three methods. The FC 5% is investigated as it can reflect the characteristic values for the glass design purpose. From the results, we can see that the FC 5% stays almost the same at the ambient temperature. However, it increases a lot at the elevated temperature. Therefore, we can conclude that there is no immediate impact for the characteristic value used for the ambient design purpose. The following steps are followed to investigate the impact of invalid tests on the test accuracy and efficiency. First of all, the available data is obtained from the experimental results, which includes both valid points and invalid points. Then 100 different sequences are generated based on this available data, and each sequence is a reshuffled version of the test results. The mean and standard deviation are updated progressively until utilizing the entire sequence of the test results. And for each posterior sample pair, a single value of an FC 5% can be obtained. After considering all the posterior samples, the mean and standard deviation of FC 5% posterior distribution can be obtained. Therefore, the coefficient of variance of this posterior distribution can be calculated for both method 2 and method 3. This process is repeated for these 100 randomly generated sequences. The graphs here represent the coefficient of variation results for both testing temperatures. The clouds here represent the COV results for these 100 different sequences. The dashed line here represents the mean value of COV across these 100 different sequences. From the graphs, we can see that the clouds, after considering the invalid points, are typically lower compared with only considering the valid points. Therefore, we can conclude that incorporating invalid points reduces the uncertainty on FC 5%. And we can also observe the clouds on the right graph are typically higher compared with the clouds on the left graph. Therefore, we can conclude that the higher test temperature may lead to a great uncertainty in FC 5%. And when comparing the two dashed lines, we can see that at ambient temperature they stay almost the same. However, at the elevated temperature, there is a marked difference or distance between these two dashed lines. Therefore, we can make a conclusion that at ambient temperature there is no advantage in reducing the test numbers, but only in avoiding the bias. And at the elevated temperature, there is an advantage in improving the test efficiency. In conclusion, the proposed methodology helps to enhance the accuracy of the glass fracture load distribution, helps to reduce the bias in the current ASTM C1499 standards, and particularly in this study, helps to improve the test efficiency at the elevated temperature. Thank you for your attention. If you have further questions, feel free to contact me.